All right, Advent of Code, day 16. Here we go. Okay. Oh, is this a max flow problem? Oh no. Let's see. One minute to follow a tunnel. What is the most pressure you could release? Oh, I see. How many minutes do we have? 30. Okay. So, interesting. I think locally greedy is not going to be right, but let me go ahead and parse this all out. Okay. Um, 6, 2, 8. Okay. Okay, so I think everything is going to be, well, let's do this. And the flow rate is going to be the only number in the line. And then the resulting valves are going to be, let's split the semicolon. Okay, I think I just want one more. Cool, so I know what leads to what. Wait, sorry. There shouldn't be a singular x, I think. Oh, I see. Because it could be valve instead of valves. Let's do something hacky. That's very hacky, but cool. And we'll simply do okay. Cool, so that works. Why are the flows 0 for almost all of these? That's weird. We'll just do recursive backtracking. And I assume are these symmetric? So, oh, wait, these should not be, oops. Cool, there we go. Oh, what happened? Yes, they are symmetrical, it looks like. Wait, 20. Okay. So what we'll do is we could from a given position and minutes left. Oh, I think we could just cache this. What is it? I think this will work. If it doesn't, then I'll fix it later. So current node and then minutes left, and so I guess first we have two options. Oops. I care about the opened set, right? Let's make it a, yeah, you can't release anything more than once. Opened is going to be a tuple, so we can hash things. Okay, and what we'll do, so we can either open cur, in which case we are going to do so first we're going to get minutes left. Let's see. It's fully to 0. 1 minute move to val BB. Okay, so you don't get the minute you spend opening it. That's fine. Times the flow of cur. Okay, so we only do this case if cur is not open. If it's not, then yep, we gather this much. And now we're going to be using uptime 2. So what we'll do is we will say for each adjacency, we're going to call it again on the adjacency. This is very hacky, don't mind me. Or sorry, not cur. We're adding adjacency to the open set. And then we are going to subtract 2 minutes left. Okay. I think that's just correct, like as is. I do have need a base case. Cool, we get 0 additional value from that. Don't open cur. Oh, whoops. I think it's just going to be this, but then we also check, like, what if we didn't open cur? If we didn't open, oh, whoops, sorry, we're not opening adjacency here. In this case, we are opening cur. Just do this. Okay. And in this case, we are not opening cur, so we just leave open as is. In this case, we only lose 1 minute walking there. In this case, we lose 2, but we don't get the value of val. I think that's right. And I guess we'll just try it. Start at AA, nothing open, and 30 minutes left. See if this works. It's chugging along there. I wonder. It definitely should be very slow. Maybe it shouldn't be this slow though. This seems fine. To do the 30 maybe? It is being cached. I don't know. Okay, so like it's kind of stuck at the bottom here. And okay, another optimization, there's no point in opening if the val is 0. Okay. I have no clue. Oh, that's an answer. Rank 1. Only take you 4 minutes, leaving me with only 26 minutes. Having 2 of you, oh no. This is going to be tricky, I think. Okay, so both of us get 26 minutes, and we both start here. Okay. This is going to be very slow. Because... Actually, will it? I think... Let's try... So, 2... Basically, we're just going to have 2 curves. The open set will stay the same. The min left will stay the same. Because these need to evolve at the same time. No, they don't. Because one of them could open and then move, and the other one could just like keep moving. That is annoying. How are we gonna do this? I guess, does it stay synchronous? Because if it's always 2 minutes, or 1 or 2 minutes. Let me think about this. Yeah, I think that this is a little bit annoying. Let's do, I guess we could alternate us move, and this will be a Boolean, and no, I don't like that either. We can do this actually. This is definitely going to be a little, oh, that'll be super slow though. Oh, I feel like I should do DP bottom up here instead of this memoized thing. If I do that, how does it change? I mean, I guess if we always simulate 2 time steps, I think that's okay, actually. I think we can just do this. We can just always sort of simulate 2 time steps at a time, maybe. So that'll mean like, so what are the possibilities? There's the things that we could do. We could, in 2 minutes, we could open move or just move move. It might be interesting to move open. So maybe we look at like 3-minute blocks or something. Does this make sense? Wait, I just think that like, no, I think like either we move or we open. This is fine. I just don't need to do both at once. Okay. So consider opening. So there's 2 cases. Like we either move open. Yeah, it's like we either both open valves this time step, or one of us moves, the other one opens, or the other one moves, or we both move. And this is just like, each of these takes 1 time step in total. So we'll just do this. Okay, so if it's not opened, then we will consider opening it. If cur2 not opened, we will also consider, so this is the case, consider open open. If we do this, then the value we get times the value of cur, plus the value of cur2, and then new open is going to be, we'll do the curse thing. Okay. And then what we need to do is we need to consider all adjacencies for both of us. Oh wait, no, we don't. No, we don't. At this point, if we both open, then we're just, the value we're going to get is just going to be it's going to be del plus recurse on the same 2 things with new opened, and 1 less minute. Okay. Otherwise, if one of us is open, and I'm just going to copy paste the code. So this is if cur has not been opened. So consider open move. In this case, we're going to get the value from cur2, and for adjacency in cur, we're going to oh, sorry. We only need to consider this if both of them, yeah. Oh, whoops, sorry. We always consider this case. That shouldn't be an if. And I'll also do like and f cur greater than 0. And f cur2 greater than 0. We need to actually like consider, it needs to be non-zero for us to even bother thinking about opening it. Now for the adjacency here, we're going to move there. So what's going to happen here? Cur is going to move to adjacency. Cur2 is going to be, so the new opened is now going to be this. We're just going to, oh, whoops, sorry. We get the value from 1. 1 is going to open and 2 is going to move. Whoops, that's my bad. Okay, so this is going to be cur adjacent. The new opened is just going to be like so. Oops, that's important. And again, we lose 1 minute. We're just always going to lose 1 minute here. Max best and this expression. Does that look right? Yeah, he moved. That seems fine. Whoops, I forgot the val. Val plus, of course. Okay. Next, what we're gonna do is consider. Oh, sorry. If cur2 not opened and if cur2 0, consider move open. I'm retyping this because I don't want to make a typo, and I think this is the safest way. Or sorry, like when I copy, I'm worried about not fixing one of the curs to cur2s. If I do this, I can sort of be very careful to swap everything. So this is gonna stay, or this is gonna be adjacent now because that's moving. Cur2 stays. New opened is this min left -1, and then finally consider move. And this might be the slowest because we have to do 2 loops. And just gonna do the best of max flow 2, adjacent 2. This is adjacent 1, by the way. That was a little scary. That could have been a bad bug. Open doesn't change. You still lose a minute. And then cool. So now what we're gonna do? Max flow 2. Both are gonna start at AA. It's still gonna be empty, but now we have 26 minutes. And are we still caching? We are. Okay. And this may take a few business days. I don't know. It's going to be really slow. I'm going to try PyPy. I have it ready. I don't know if it'll be faster or not, because I don't know how fast like this caching is. I imagine it's not fast at all. Let's see. I kind of just have no choice, but I think to let it run. How many possibilities are there here? There's like a lot, is the thing. It should always be going down by 1. Maybe I'll add some prints. I'm a little scared about like restarting this though. But I have to know like, yeah, let's do like, so we're starting at 26 now. So maybe like everything 23 and up. We'll just print this. Ooh, that is really slow. If it's never recursing back up to 23 at this rate, I wonder if I need another approach. This sort of thing is definitely not very nice, but I wonder what the slow part of it is. Let's see just how bad it is. That's really bad. So here's another thing we can do. If we have a cache entry for the same thing, but with strictly more time left, we just don't even need to consider it. So I'm gonna make a custom cache. And what we'll do is if cur2 opened. So for a given value of this, yeah, let's have the cache point to like, if it's in, okay, if it's not in the cache, or it is in the cache, so the cache is going to point to hit 15 again. Wow, that's extremely slow. I'm going to let this one keep running, the PyPy. I don't think it's going to finish. Even at a few orders of magnitude speed up, it still would not finish in any reasonable time. But anyways, this is going to point to like largest min left, and then like the actual result. And what we're going to do is we're going to say if the min result, or yeah, sorry. So if it is in the cache, and we have more time left than we did last time we saw this entry in the cache, then we'll recompute. Whoops. Okay. And then the return here is just going to be, honestly, we can just scoop this up here. I think that's fine. I'll leave this, and what we'll do at the end is we'll just say cache of cur2 opened is equal to, what are we going to put in here? We're going to put the time we saw because it was greater than, and then we're also going to put the actual value, and we're going to return what's in the cache. Cool. And see if this is any faster. Whoa. That is because I called it cache too. It's called a cache. It might complain about a global. Oh. Cool. Doesn't seem much faster. Doesn't seem any faster. Seems slower. Maybe. I guess we can see if it does anything. Oh man. What's the leaderboard looking like for this? No one's gotten both stars yet. Okay, so this is a tricky one. Is there an algorithm that I could be missing here? I mean, there must be. We're moving both of these. So something that we can do, we could maybe just optimize out like every size 0 flow rate. Like we could compress the graph a little bit. There's actually only a few nodes with non-zero flow rates. So maybe it's even worth computing by hand. This seems actually quite feasible. I think I want to, okay, so this is set depth 13. It's never going to finish. I think I'm going to try compressing the graph. So here's what we'll do. We will say, I'm just going to do the whole graph compression in terminals. So we have the graph, right? And make the new graph. And the idea is going to be, we're just going to check each one of these. And if it's flow rate 0, we're going to compress it. So the new graph is going to be a default dict, and it's just going to be a distance. And what we'll do, because I think these are symmetrical for the graph, we'll do like start location and this, and just assert x in g of y. Make sure that it's symmetric. Okay, it is fully symmetric. That's good. And g of xy is going to be 1. Cool. Yeah, I think that's just right. So all the edge weights right now are 1. And now we're going to say for node in G, if the flow rate of x is equal to 0, compress. And the way that we compress is we're going to say, we can do it in a very inefficient way. Actually, this is just fine. Every adjacent, so we're going to do for yes, okay. For y in yeah, sorry, for y in g of x, for y2 in g of x, if y equals 2, we'll just skip it. And then what we want to do is we're just going to say g of y2. Sorry, what is the default dict default to? It defaults to 0. That's not good. So the default distance for any two things should be infinite. That 100 is infinite here because it takes us, we only have like 26 minutes anyways. Cool. And then I lost my alt code. That's lovely. Doesn't take that long to write. And then the new graph. I actually think I want to be compressing in the new graph. The new graph of y1 to y2 is the min of whatever it was before, and the distance from like y1 to x plus the distance from x to y2. And this is symmetric, so the order does not matter, but just to help me keep things straight. And then finally, so after we've done this, I think we just want to delete x from ugraph entirely. So what we'll do whoops. Sorry, this does not work, but this will. If x, x2 new graph, and then similarly, do the opposite direction. It's unfortunate. What went wrong? Oh, whoops. That seems fine. Why is this not working? Seems fine, maybe. Oh my god. Okay, we're gonna get rid of this step, I think. That's not good. Oh, I see. I think we just have it in like G, right? Yeah, and now we can just do this. Get rid of this condition. Partially because of the state. I already messed it up. And then we're just gonna look at other things. Yeah, cool. And then, whoops, I don't want to look at that. This will be really big, but the beauty of it is, we can just only keep elements where this is non-zero and non-zero. We're a little bit screwed because I messed up. Wait, sorry, what? What did I do wrong here? Okay, one. It thinks something's a string when it shouldn't be. Okay, I'm gonna rewrite. It's the best way to do this. Why can I not compress a graph? Why am I bad at this? Oh boy. Okay, so here's what we'll do. So this just computes the adjacency matrix, basically, right? Or sorry, like the distance matrix. Let's actually just do, yeah, so we'll do like, and cool. This gives us these points, and now I think we do like I think we do like n iterations of this. So I think we called it KZ, and we'll just do and well, select the distance from 1 to 3 to be the minimum of this, and distance from x1 to x2. This is basically what I was doing before. I'm doing it maybe a little more conventional way now. I think I did not need this outer loop. This seems fine. Okay. I definitely did self-connections. What does it have for this entry? That should be dist. It's 2 for self-connections. I will just remove self-connections. And the next thing I will do is I will only care about elements with non-zero flow. If it's greater than 0, or it's AA, because we start there. The keep is only 16. That is more than I thought it was, but I guess this is a thing. I don't know if I can do this manually. It seems painful. But, okay. We have this now, and I think what we'll do is we'll just do A, B, and then dist from A to B for A in keep, for B in keep, if A not equal to B. I think that's sufficient. Cool. And now, yes, so these are all the connections. What are we going to do now? And so like each one is now the cost to traverse this. So what can we do? I think we can sort of think of each of us and the elephant independently. That's not true. People get it yet, by the way? Oh, some people got it. Oh man. Wow, it's been 30 minutes already? That's crazy. Cool. So first of all, what's actually reachable from AA in reasonable amounts of time? Also, I'm just gonna save this in case I mess it up again. Yeah, that seems good. Cool. And let's create like a different style of graph. Yeah, let's do like this. I think I called it keep, right? What we'll do, and for y in keep, x equals. We're just going to add in the cost. Is this too? X to y, and then y. So now we can do something like this and see where we can get to from here. Okay, and then from each of these, like from OT, for instance, we can go to all of these. That's neat. How many? There's going to be like a lot of paths thing. What's a true statement? Does it ever make sense to walk back to a node that we've already walked past? I think it does because of the way that the flow works. We might want to walk to something that's really expensive to turn it on and then walk back. So that's out, that idea. What can we do here? By the way, I'm going to also copy this in here. Just because I might want to run it with PyPy. Yeah, how do I approach this, man? I must be missing something pretty, I don't want to say obvious, but something that I should be able to come up with here. I mean, yeah, these are like, because the ordering matters too is the problem. There's no way to think of this as like a Dijkstra's or something, I don't think. Okay, so what is true? So like we could do some sort of DP / memoized recursion, where we have like our location, our time left, elephant location, and then elephant time left. And if we do this, this seems fine. But then we also need to care about like which things have been turned on. Open vals. This is going to be pretty similar, except I think I'm going to use the new graph formulation for it. So what we'll do, yeah. I guess I'll just try and write this. I don't know. I think this is something in Python that is like a hashable set, but I don't know what it's called, and I think I would lose time looking it up. I might look it up actually if this is slow. Okay, so if our time left is I guess we can do, wait. Yeah, we can either move, so we have two options here. We can either yeah, it's like us move, us open, elephant move, elephant open. Each of these is like one transition, and we care about like the best value we can get from any one of these operations. So for this, let's consider us move. If we do us move, if our time left, well, I guess we'll just do this for adjacency in G2 of our location. Sorry, like cost G2 adjacency. If the cost is greater than, so it doesn't make sense to walk anywhere that that like we won't have time to turn anything on. So we actually care about the cost. Actually, like, let's see, if we have like 3 minutes left, even if we walk somewhere in 2 minutes and then we open the valve, we get nothing from that. So I think it needs to be larger than 2. Our time left needs to be larger than the cost plus 2, or is it greater than or equal to? Let's see, if cost was like 2 and our time left was 4, are we happy? Yeah, we're happy. We get one time unit of flow. If this is the case, then we will consider moving. So it's going to be adjacency, our time left minus cost, elephant location, elephant time left, open valves. We didn't open any valves, we just moved somewhere. Next, let's consider if we open the valve. If we open the valve, what do we get? So if our location not in open valves, what we get is we're going to profit for our time left minus 1 times the value of our location, plus the recursive call. And what happens in the recursive call, it's just going to be our location doesn't change, our time left goes down by 1, and nothing else changes. Open valves does, let's do this. Oops, sorry, I'm scrolling down a little bit. Open add valve, open valves, new valve. This tuple set thing is just so it's hashable, or this tuple sorted thing. It's hashable and it's also like keeps in the right order. It's a little bit cursed. Sorry, it's like really cursed actually, but you know it is what it is. And I'm too lazy to look up what the proper Python hashable set is. Okay, and we're gonna add open valve, add valve. I'm just gonna call it add. Open valves, and then our loc is what we're adding here. Cool, I think that's right. Oops, I need another parenthesis. Okay, and then now I think everything is the same except for the elephant. Oh, and I guess I also need to mention, and let's do this other check first, actually. We need our time left to be larger than 2. Or greater than equal to 2. And I think now we're just going to replace every hour with elephants. Okay, that's going to mess things up. That was a mistake. I don't know why I did that. These all stay the same, sort of. The -1 happens on the elephant time now instead of ours. And elephant time left -1. That is right. This seems right. What about this? Sorry, our location doesn't change here. Our time left also doesn't change. The elephant location does change to adjacency. Good, we're doing elephant location. And the elephant time left does lose cost. And the open valves does not change here. And we return the best. Cool, and let's see. Oh no, it didn't copy right? That's not good. Oh, did I paste it twice or something? Oops. I definitely defined keep up here. Okay, let's run this maybe. So for starters, let's run it at like, if we only had 5 left. Okay, that's an answer for sure. It's probably too slow, but we'll try it. You never know, you know? Now we're back to the waiting game, I guess. I am going to do a progress checker. So let's do so this will do like a obnoxious amount of printing, hopefully. Yeah. Something like this still does quite a bit. Wait, it definitely should not like, oh, sorry, this is like 10 each. This is like 15 each, I think. That prints occasionally. That's still way too slow. Oh, man. So I guess, no. Thought about like dynamically compressing this. This is so tricky. I am very tempted to just look up the algorithm because I feel like I can find it if I Google properly. Like this is just way too slow because like we're starting this off with 2 times that add up to 52, right? Which is like just really crazy, like crazy large in comparison to this. And like every time I increase this by 1, I should see prints like exponentially less often. So it's basically never going to finish like this. Something we can take advantage of is like we only care about when the time is like at least this good. The open valves to here. Let me actually think what the size of this memo table is. Maybe we could bottom up it if I don't think that would help. But so open valves, I think there's we only consider everything in keep. So that's like pretty small dimension. The problem is the other dimensions. So this can be like 16 times our time left can be any number that is between 0 and 26 times 16 times 26 times 6.536. So that's the number of entries in this table. And I think approximately all of them need to be filled out. So that's too many. I'm wondering if it's some trick of like using time as a dimension here. And like, that doesn't seem right though. Two sources. I actually don't know how to describe this problem very well. I've definitely seen something like it before on Code Forces or something. Nah, it's not a graph problem. So I don't think that's not tractable either. I keep thinking like we could consider each possible set of things that get turned on eventually. But even if we do that, like the ordering that we turn things on in matters quite a bit. So that doesn't seem like it'll be helpful. Oh. I think for like a given amount of time, it's not that hard to find. Or no, that's not true. I actually just don't know the algorithm here. Sorry for being so quiet. I'm just like, just thinking and having a hard time thinking of something reasonable to do here. I mean, like, how big would this table be if we were able to like half each of these dimensions? I know we're not able to, but that's still way too big. Now, if we could get rid of one of them and just do this, that's still pretty large, but I think it's maybe doable in like enough time. I don't know. Let's see if this crashes. Keeping a list is pretty expensive. Yeah, I think I'll run out of memory if I do this. We could certainly like do some sort of heuristic and say you never go back to a location you visited before. That's definitely not going to. I mean, it's not going to be correct for sure. Just so I know to remove it. I don't think this would speed things up that much, actually, but we'll try it. Yeah, it's still abysmally slow. I mean, I guess something we can do, like we can think about what the most valuable things are starting from A and maybe like make some guesses. This is where we can go from A. And of these, wait, whoops, what do I care about? I called it like G2, right? These are the places we can go from A. And what we'll do, so what are the flow rates here? Can we get to Vx? That costs us 8. It costs us 8, but it locks in quite a bit. So we can do things like, we can, so let's get rid of this. Get rid of this. So we could lock this in. We can say, what if we go, straight to Vx to grab that 25? I'm actually just going to predict this. Cost efficiency G2AA. Let's sort it. Print cost adjacency, the value of the adjacency, and like, I don't know, let's do this for starters. Yeah, so this looks pretty good. Oh, I think the OM actually, because this is like much closer. Someone's definitely going to OM first. So I think that's a 5 for free that we can just get. What if we assume go to OM and VX first? So what are we going to do there? We're going to spend 5. I'm just going to make sure I get the time right. So of our 26, initially it's 26 and 26, which is 52. And if we go to OM, that's going to cost us, let's see, OM. And we are now going to have, that cost us 5, so 21 left. The elephant is going to go straight to VX, and that is going to mean that the elephant has, oh, by the way, is this a dense graph now? I guess it must be. Oh, shoot. This is not right. This assumption is not very good because we are probably going to be passing through something else on the way there. And I didn't keep track of the paths anymore. So the Vx we can get to from Zi or AL. Looking at the original graph. It's pretty far away, actually. Oh, it's not going to work. Does it help knowing that like this is a dense graph and we can go anywhere at any time? I don't know if it does. Wait. Maybe it does? So each of these is going to be like at least distance 2 away. So 26, 13 factorial. No, that's way too large. 10 factorial is like even pretty large. It doesn't work. I was thinking like, what if we just look at all paths we could take, all paths the elephant could take, and just try them both? Another thing we could do is we could consider like these paths independently, then inclusion, exclusion. I've been toying with that idea. I don't think it works. Wow, this is a tough question to follow up after yesterday with. Oh, and it's not even the weekend yet. Yeah, we can consider orderings of like, oh, I guess here's a statement that's true. Let's do this. Let's do like get orderings, or like get paths. Sure. We'll have like a location, and we'll have like a budget. And basically, what we'll do is we will say for path and get paths. So like, there's a few places we could go. for cost adjacency into location. If cost is greater than, I think we could just use this condition. If budget is greater than or equal to cost plus 2, then we'll consider it. And what we will do is for every path in the paths from here, by the way, this is not the efficient way to write this. From adjacent with budget minus cost, minus 1, because these will only be paths where we activate each stop, except for the first one. That sounds reasonable, I think. We're just gonna yield like location plus the rest of the path. Cool. And now I do want to keep printing this, by the way. This is just, I think, helpful to look at every time. Let's look at the paths from AA. The budget of like 5. Sorry, I want to look at the paths. How many are there? There's none. That's wrong. That is very wrong. That is because if budget is, if it's 1, right, then we can just yield the current location. I think that's right. Do we want to be able to terminate our path anywhere? I think we do. I think this will give us a few extra paths that we don't want, but yeah, so if we have a budget of 5, these are the places we can go from AA. We can go to OT in 3. We can go to YW directly. I don't think there's any double paths. Let's look at 6. And here's another fun fact. Exclude is going to be a set. I'm going to write this in a not efficient way because I feel like it. And exclude, we're going to add the current location. We never come back to our current location. And here, that's fine because, sorry, I'm going to get rid of that for a sec to make sure that my change actually works. Because we're only looking at the places where we actually activate, where we actually open the thing. So here we have a path where we go back to AA, but this doesn't make any sense because we would never actually want to, well, AA has 0 flow, I think. That's true, right? Yeah. But still, we never want to like go to AA. We're happy to walk through it, but we don't want to go to AA in the sense of like go and activate. Cool, so the length of 7, that's unfortunate. That is because I forgot to actually write that. Nice, and now we never go back to the same place. And now we can just sort of see how many paths there are. I suspect it'll blow up too quickly, but it might not. That is not right. Whoa, what happened? Get paths. This is a bug. Bug. It's a classic one. Gets everyone at some point. No, what am I doing? Oh, okay, that is a sillier mistake, which is that I need to add 1k. Oh, that's not that many paths, actually. That is a totally reasonable number of paths. Okay, this is cool. So we can just look at all of these squared. Well, we can kind of look at all of these squared. And for each of these paths, like we'll look at each one for us and each one for the elephant. And we'll just like for each path, we'll compute like what would the value be. This is still pretty slow. I think this is going to be a bit too slow. If it didn't have like an extra ugly constant factor in front, maybe it would have been reasonable. But yeah, this is like the number of paths for length 26 starting from AA, I think. Yeah, even 25 is like significantly more feasible. I mean, it's still not that feasible, but it's so funny that I keep trying to come up with other clever ways to brute force this, and like, there's still kind of brute forcey ways, but I'm sure there's actually just like a clever algorithm that runs like efficiently here. I bet it's also implemented for you in like Network X, but I don't know what it is. I'm gonna be really sad if it was just like, there's no way it was just this DP. Okay, let's maybe proceed with this idea. Yeah, okay. So let's just do like, it's easy to tell ourselves what the value of a path is. The problem is when we overlap two paths, can we do a clever inclusion-exclusion here? I don't think so. I actually am a little curious what the... So just for insight reasons, let's look at a path. If we have the value of a path, well, we are going to say just look at every pair. And what we're going to do is we're going to walk from A to B and then turn on B. And we like a time. Sorry, when I say turn on, like open valve B. Right, so we will do I would like to get this graph in a different form. I think it's already in this form, right? If I look at it like this, yeah, cool. So the distance from A to B, we just use that, we burn it, and then we burn 1 to turn it on, and the result we're going to add the value of node B times time. Cool. I'm just interested in seeing how much time we have left as well. I'll just look at like the 15,000th path. That's a path. And let's look at the value of this path. If we had time 26, that's a little sad. I'm not going to rerun everything. Cool. We had three time left at the very end, and if we look at the adjacencies to ZL, in theory, yeah, like there's nothing we could profitably do with 3 time left, right? Because we could move to IC and then we could turn it on, but we wouldn't get any actual flow from it, I think. Needs, that's 704. And now I think we just do like, I mean, this, again, this is like just for my curiosity. But like path 26 for path and get paths, A 26. So the best single path is 1302. Does that line up with what we had here? No, and that's because we actually had 30. This actually should just be like a way of doing part 1. Was that what I got? Yeah, it was. Okay. So like here's a alternate part 1. I'll just leave that in there. Yeah, but cool. So if we did like, ooh, if we look at 2 paths. So here's a question. Oh, maybe what we can do is like, no. If we fix a path, is it easy to find like the highest value complementary path? I actually think it might be. Yeah, because we just don't want to. Wait, this is actually maybe good. So here's what we'll do. For path 1 in get paths of, yeah, I think this is a good idea actually. I think this might work. Starting from AA, budget 26, and then we're actually going to exclude nothing. I'm writing this explicitly for a reason. The idea is that now, We just want to exclude everything in path 1, right? So this is also going to be 26, but we're just going to exclude everything from path 1. So exclude is going to be set of path 1. And let's just keep the counter. This will be way smaller than the actual like square the number of paths. Shoot, what does it look like? Set of path 1. What does path 1 look like? I don't know why it doesn't like that. We're adding a location. This seems fine. This seems what's wrong? It thinks exclude is a dict. Why does it think that? Oh, classic. Maybe it is pretty slow. It's slow, but not unbearably slow. This just needs to make it to like 4,000 or so. This could work. Because now these paths are just already mutually exclusive. I can just do P1b is going to be the value of path 1. It's certainly slow, but it's not horrendously slow. P2b is going to be the value of path 2. It's going to slow down a lot now, but I expect that. Whoa, what do these look like this? Oh, whoops. It's because I don't care about this anymore. It's pretty slow, yeah. Where is my PyPy window? Oh, I forgot it was still running this whole time, the PyPy on the old input. But if I do this now, it is a lot slower. It's speeding up, maybe? I'm pretty sure CPython will finish faster, though. Do I even bother letting it race? I don't really know if it makes a difference. Hopefully I don't have any bugs in here. That'd be pretty sad. Oh, is it catching up? I don't think so. I think it's like a constant amount behind. But I don't think letting it run is going to slow anything down. So it'll be my insurance. Oh no, it did catch up. It's catching up. And it's passing it. Sweet. Oh, but I'm printing out the counter at the best value. Okay, so this run is dead anyways. Because like it's not going to print out the best value for me. I have to like actually evaluate it here. Is it 4,800 or 40? I forget what it was. I probably won't leaderboard. I think I've probably passed the time, but wait, what? There were 5,000 paths? Oh, were there 48,000 paths? I think there probably were. Well, this is definitely going to take a while then. But I can definitely add print best value. And I can let PyPy run as well. And I can try other like speedups maybe. Like what? I guess this could be cached. This is a tuple, but it has no reason to be. It could be a list. I don't know if that by itself will speed anything up, but then we can maybe LRU cache this one. See if that's any faster. Is it? I can't really tell. It seems like it's accelerating. I guess because as the cache fills up, it already knows what things are. I don't know. Yeah, I don't know. Let's open another. I want to like test things, but I don't have another terminal window, so. Okay, so I'm definitely not going to leaderboard now, by the way. I didn't realize how slow this was. Like I thought it was going to 4,800, not 48,000. But let's do day 16. Oh my god, not what I wanted. Okay, cool. I think if I do this, and then I can do, wait, really? I'm only adding this so I can import it. Cool. And what I'm interested in now is, yeah, it was 48,000. Yeah, this has got a little ways to go, for sure. It's not printing fast enough that the print is a slowdown. Actually, maybe in this one it is, but... Oh no. Okay, sorry. I was apologizing for my code there. Yeah, we have time to check this now. Yeah, capped. I mean, okay. I did get number 1 for part 1, which I'm really happy about. This is, I think, my first ever number 1, maybe? I might have gotten a number 1 at some point before. I don't think I did, though. I think I've gotten a bunch. I've gotten a couple number 2s and number 3s. This moved me up 1 place on the global. Okay. I definitely have, like, private leaderboards that I care about, so I definitely do still care about finishing this quickly. I'm going to be really sad when I look at the subreddit and see the simplest solutions. Looks like PyPy is catching up. Just a waiting game now. Oh. I was going to say there could be a speed up where, like, because technically it'll consider the same path but, like, reversed, so it's, like, twice as slow as it could be, right? Like, for every path 1 and path 2 it considers, it will also end up considering the opposite. I don't know if there's actually an easy way to fix it from doing that. Like, obviously I could add something like, just compare them, like if path 1 greater than path 2, continue. This is, like, pretty silly, and I don't think it'll actually speed it up that much because I'm pretty sure get paths is the slow part and not value. But that's, like, a thing that I could do. Okay, so the PyPy has officially overtaken the CPython one now. And it's, like, halfway there. I don't know. We're at, like, an hour and 12 minutes. Whew. What was the last time on here? Oops. On day 16. It was an hour and 4 minutes. Wow. You know, PyPy is ahead, but not by much. By the way, just, like, something that I think is kind of interesting. The reason why it slows down, I think the reason why it slows down is because path 1 can variously be either long or short. Getting all the paths of length 26, like, it does produce them in a certain order, but not in order of increasing or decreasing, like, number of things. And I guess I'm not really sure. I guess when it's doing a full inner loop, probably when path 1 is smaller, this takes longer because there's fewer things being excluded, so there's more path 2s. Yeah, so, like, the slower it goes, the shorter path 1 is probably. That's probably also why it's so slow at the beginning, because the very beginning things are, like, the 1 and the 2 element paths. But yeah. Ooh, 33 out of 48. Just gonna let it keep going. The saddest thing here will be if there's, like, an error at the very end and it doesn't print out the answer. That would be very sad. Come on, another 10K to go. Oh, it'd also be pretty sad if the answer is wrong, which maybe is higher likelihood. I wonder if get paths could have been cached. I don't think it would have been that much faster. 48 something? Come on. Come on. Alright, that's an answer. Wait. Oh, sorry, that's the counter. This is the best value. It's 2207. Please. Oh, what a relief that that was a correct answer. Rank 147. Okay. Oh man. I'm not gonna let this finish. Whew. Tough question. Wow. I think that has to be the toughest one of the year, I think. I guess the toughest one of the year usually does come around like 16 or so. I think, what was it last year? Was it like 19 or something? Oh yeah. This one was the one that I think you kind of just had to use like a constraint solver for this. I don't think you maybe had to, but I think it's how I ended up solving it. And I'm pretty sure, yeah, so 19, 2021 was, yeah, that was also an hour and 4 minutes to fill up the leaderboard. Kind of crazy, it's a hour 4 minutes both ways. Just thinking about that makes me wonder if I could have solved this one with a constraint solver. Probably not. I think, well, maybe. Could I? Maximize? Maybe. I don't know. Cool. Okay. Well, I think I was kind of explaining my approach while I was writing that and while I was waiting for things. So I'm not going to explain it again. And also, it's pretty late. So I think I will just call the recording here. Overall, like I'm fairly happy with number 1. Even if I didn't make leaderboard in part 2. But yeah, that's it for today.